Okay, let's continue with finding the expected value of a random variable with this experiment. Suppose a random sample of 2 light bulbs is selected from a group of 8 bulbs that contain 3 defective bulbs. What is the expected value of the number of defective bulbs in the sample? Now, here, since we're interested in the expected value of the number of defective bulbs, we're going to let X represent the number of defective bulbs that occur on a given trial. Now, if I were to randomly select 2 light bulbs from this group of 8, even though there are 3 defective bulbs in the sample, there's no way that I can get 3 bulbs that are defective because I'm only selecting 2. So when you're working these problems, make sure you not only know how many you're sampling, but also how many of the items you're interested in are in the sample. So here I can't get more than 2 defective bulbs. So I can get 0, 1, or 2 defective bulbs. Now let me just present you with a situation. Suppose I only had 1 defective bulb in these 8. Well, then I couldn't even go as high as 2, because even though I'm taking a sample of 2, I could only get as high as 1 defective bulb. So you have to pay attention to the numbers that you have, not only in the number you're sampling, but also the number of items that are in the sample. Okay, so now let's talk about the probability of getting no defective bulbs. So to get no defective bulbs, first of all, we know the total number of samples would be 8 choose 2. That's how many samples are possible. And then to get no defective bulbs, that would mean out of the 3 bad bulbs, you choose none. And out of the 5 good bulbs, you choose both bulbs from those. That came out to be 0.3571. Next, the probability of getting 1 defective bulb. Well, that would mean out of the 3 defective bulbs, you choose 1, and out of the 5 good bulbs, you choose 1, divided by the same denominator. That gives you 0.5357. And now finally, the probability of getting 2 defective bulbs. That would mean out of the 3 defective bulbs, you choose 2, and out of the 5 good bulbs, you choose none, and then divide that by 8 choose 2, and you get 0.1071. Now I can fill out the probability distribution table because I know the probabilities, and then once I fill out the table, I can calculate the expected value of the random variable by simply multiplying 0 times 0.3571, 1 times 0.5357, and then 2 times 0.1071, and then add these together, and I can get that the expected number of defective bulbs in a sample would be 0.75. So we would expect to average 0.75 defective bulbs in a sample if we did this experiment a large number of times. Let's do one of our lottery games. In Texas, we have a game where you choose 6 numbers from the numbers 1 through 54, and there's no repetition allowed, and the order you choose them does not matter. You just choose 6 numbers. Now, I'm going to let X be the number of matches that you get on your ticket. So if you match 3 numbers, X would be 3. If you match 1 number, X would be 1, and so forth. So let's think about what you could match. Now you obviously could match none of the 6 numbers that are selected up to 6 of the 6 numbers you selected. Now obviously if you did that one, then you could probably quit work and take care of all your friends and family. So really there are 6 good numbers that we don't know what they are, but there's going to be 6 good numbers that we like, and there's going to be 48 bad numbers. So let's look at the probability of getting no matches. The probability of matching no numbers would mean that out of the 48 bad numbers, you chose 6. So you figure out how many ways can you choose 6 bad numbers out of the 48 bad numbers, and then you divide it by the total number of 6 number combinations, which is 54 to choose 6. So that's 0.475. And then the probability of 1 bad number would be 6 out of the 6 good numbers, you choose 1. So I'm sorry, that's 1 good number, not bad number. So the probability that you get one good number would be out of the 6 good numbers choose 1, and out of the 48 bad numbers choose 5, and you divide that by the same denominator and get 0.398. The probability of getting 2 good numbers would be out of the 6 good numbers choose 2 and the 48 bad numbers choose 4, divided by 54 choose 6, that's 0.113. And notice the probability is getting smaller and smaller, huh? So the probability of getting 3 bad numbers would be 6 choose 3 times 48 choose 3 over 54 choose 6, which is 0.0134. And you can go on and do the rest of this. For 4, it's 6 good numbers choose 4, 48 bad numbers choose 2, and then divide by the denominator. For 5, it's 6 good numbers choose 5, 48 bad numbers choose 1, divided by 54 choose 6. And then for 6, you get 6 choose 6, so that would be 1, because there's only one way to get the jackpot out of 54 choose 6, and that's a very, very small number. Now, if I calculate the expected value of the number of matches here, I just multiply each of these together and then add the results, and I got 0.667. So we'll just say 0.7. So this means that the average person that buys one ticket matches 0.7 numbers, less than 1. So the average person is going to match less than 1 number. Now, since you only win if you match 3 or more, you can see why this game is lucrative to the providers. Here's another game example. Suppose you have 1,000 raffle tickets sold at a price of $5 each. Let's say you have 2 first place tickets drawn with a prize worth $200, 5 second place tickets drawn with a prize valued at $100, and 10 third place tickets drawn with a prize valued at $50. Find the expected value of the net gain to the consumer. So now I'm looking for the net gain to the consumer. I'm not looking for the number of tickets or anything like that. So let's let X represent our net gain. Now, here's where you have to be careful. You've got to remember that you pay to play. So if you don't win anything, you actually lost $5. If you win the third place prize, you actually only won $45 because you paid $5 for the ticket. And if you win the second place prize, you only won $95 instead of $100 because you paid $5 for the ticket. And if you win the first place prize, you only won $195. Now, to calculate the probabilities, it might make more sense if we work backwards. So the probability that you win the first place prize, if you read the problem, there are 2 winning tickets out of 1,000. So the probability would be 2 out of 1,000. To win the second place prize, there's 5 winning tickets out of 1,000. So the probability would be 5 out of 1,000 that you win that. And the third place prize would be 10 out of 1,000 because there's 10 winners for the third place prize. Now, if you'll notice, there's going to be 10 plus 5 plus 2, that's 17 tickets that are going to win. And so the rest of them are going to lose $5. So let's count how many are going to lose. Take that 17, subtract it from 1,000, and you get 983 losing tickets. So the probability that you will lose $5 is 983 out of 1,000. So now we know you'll lose $5 with a probability of 0.983. You'll gain $45 with a probability of 0.01. You'll gain $95 with a probability of 0.005. And you'll gain $195 with a probability of 0.002. The expected value of this game now would be negative 5 times 0.983, 45.01, plus 95 times 0.005, plus 195 times 0.002. And this is actually a negative number, negative $3.60. Now, it makes sense that this is negative because, you know, if somebody's going to raffle off something, then they want to make money, so the consumer should lose money. So the average consumer is going to lose $3.60 per ticket. Of course, some people are going to gain, but if you consider it as an average, the average person loses $3.60. Now, if the payoff had been 0, this would be called a fair game. But since the payoff is not 0, the game is unfair. It's obviously slanted toward the people that are running the game. And that's generally the way things are going to work, especially in casinos. Okay, now quality control problem. A carton of 20 batteries contain 2 dead batteries. A random sample of 3 batteries is selected and tested. Let x be the random variable associated with the number of dead batteries. Find the expected value of x. Now I did one similar to this earlier, so this is really just kind of a repeat. So you can only have up to 2 dead batteries in the sample because there's only 2 dead batteries in the sample. So the probability that you get no dead batteries would mean that out of the 18 good batteries you chose all 3, and out of the 2 bad ones you chose none, and then divide by the total number of samples, 20 choose 3. The probability that you get 1 dead battery would mean out of the 18 good batteries you choose 2, and out of the 2 bad batteries you choose 1 over 20 choose 3. And then the probability that you get 2 dead batteries would be out of the 18 good batteries, you're going to have to choose 1 because you're choosing a sample of 3. And then out of the 2 dead batteries, you're going to choose both batteries from those. And then again, divided by 20, choose 3. And then if you multiply 0 times 0.716, 1 times 0.268, 2 times 0.016, that will give you 0.3. So you're expected to average 0.3 dead batteries per trial. So you could work backwards and determine that each batch should average, that this is what you should average. And so if you're doing this formula, using this formula, you could use this to determine the tolerance level in a quality control problem. I'll do one more on this video, and then I've got a couple of game examples I'll do on the next one. Here, a concert producer has scheduled an outdoor concert. If it does not rain, the producer plans to make $20,000 profit. If it does rain, the producer will be forced to cancel the concert and lose $12,000. The producer has learned from the weather service that the probability of rain on that date is 0.4. Find the producer's expected profit. Okay, so there's only 2 things that's going to happen. Either the guy's going to lose $12,000 if it rains, or he's going to gain $20,000 if it doesn't rain. So if it rains, he loses $12,000, and the probability of rain is 0.4. And if it doesn't rain, he's going to make $20,000, and the probability of not raining is 0.6. So if you multiply negative 12,000 times 0.4 and then 20,000 times 0.6 and add the 2 together, you get $7,200. So the expected value suggests that the vendor should not cancel because he's expected to profit $7,200. But remember, this assumes this is an average. So this would be on average he should not cancel. So if he's just got 1 concert, he probably wants to be very careful. But if he's got maybe 20 of these concerts, then he should be okay because that's a large number of trials. So even though some will get rained out, several others should make under these same probabilities. So I'll do the last couple on the next video.